How's it going, everyone? We'll get started now. Got started a little bit late, but it's such a nice day. We're trying to see if more people will roll in. So thanks everyone for coming. Today will be a great presentation on modeling the unseen.
Yeah, great.
That's good.
We're welcoming Hans from Kierkegaard, who is joining us today. And we're going to try to keep it very informal and panel-like. If you're speaking too much, then we will get bored also. So we're going to be asking and trying to be as engaged as possible with you guys. So the tonight's topic is how we implement various modeling methods for specifically acoustics and energy disciplines. And both are unseen. And I guess there are more things in common between them, but that's the thing we're sticking with for the title. And we're going to be discussing how subjective these things are, mostly to the client and also to the occupants of the buildings that we design. So who are we? Hans.
I'm a consultant with Kierkegaard Associates. I work in sort of all of the acoustic subdisciplines of mechanical noise control, acoustic isolation, and room acoustic design. We'll spare you the more, I guess, uninteresting ones and stick to room acoustics today for three-dimensional modeling. But yeah, that's my background.
And I'm an energy and data analyst at Grapple. And I see some of their analysts from various consultants too. So, well, we are Chicago Computation Group. Anthony is our moderator and coordinator and all the titles above that. And Kierkegaard and Grapple met for this building, which was Experimental and Performing Arts Center at RPI, upstate New York. It was such an exquisite design that we're proud of. We Grapple did the MEP in structure and sustainability, and Kierkegaard helped deliver this superb acoustical space for the Performing Arts Center.
And here's an example of, this is by Amir's old seat in the office, the physical scale model for this project. So not what we're going to be talking about today necessarily, but because it was a big enough project, we had the opportunity to put together one of these scale models.
Yeah, which we're going to talk about scale models and digital models and all of that. And we did not build a physical model for this project. It was, now we're looking at the screenshot of what we did for CFD at the time. And this building was completed in 2008, and it's been operational. No complaints, no nothing. So successful design. Well, we are not here to talk about that building. It's just the history of how Grapple and Kierkegaard connected and are now sharing office space. Well, we're here to talk about acoustics and energy. And they're like, when we say acoustics, it's just how sound moves across the room and propagates, and energy is how energy basically just bounces from places and provides thermal comfort if implemented such. But more likely, before we get into the modeling, we're also here to talk about when we need to resort to modeling per se, and when do we not want to model. So this is about also not just our experience, also we're waiting to hear your experience and when you choose to model something and when you choose not to model something.
I think, yeah, there's a lot of conversation, I think, sort of in all of our worlds about modeling as the tool of the future and how we're going to, keep moving forward and really understand building design. And it's going to solve all these problems, but I think it's an interesting conversation to have as to how we're going to solve those problems with modeling. Right?
So as you all know, it's just a representation and approximation. Anything that can be represented by an approximation can be modeled. And basically, almost all models are made to avoid cost and mistakes for implementation. Some are just made so that they look pretty and they have their place in the universe. And they're made up of parameters, inputs, outputs that we're all aware of. But all models are wrong, and some are useful. And as consultants, we hope our models are useful. That's why we have the choice to model something like that. Right? So we're not modeling for modeling's sake. If we know that there can be some positive impact on the design, if you're modeling to solve problems, then the model has met its true purpose. But modeling right now is made up of a million things. If you just do a quick search on LinkedIn, you'll see all sorts of modeling that you might or might not be aware of or familiar with. For instance, what the hell is a PBPK model? Right? So for sure stands for something in financial or in another world. But right now, our industry, construction, architecture, engineering, whatever you want to call it, is not the only one making models. Almost every discipline in itself is making their own models to either predict, simulate, and do something with them. And then the more bigger the stakes are, the more time goes into model, into research.
Okay. So sort of jumping out with acoustics as the first topic. Basically, what are we actually trying to model when we're thinking of an acoustic model? Or what are we trying to design? So any like the room that we're standing in now, you're hearing voice directly from my location as the direct sound, but my voice is also sort of dispersed throughout the room. So what we want to try to understand when we're looking at designing a room is how sound that reflects off of the wall or the ceiling all combine at your ears to make this sort of this spectrum of sound with various strength and timing of those reflections. So I'm sure you've heard of reverberation time, which is sort of the longer term duration of sound, and how long it bounces around between reflective surfaces. But again, the timing of those other reflections really are a crucial part of how a room sounds, and also largely what we're looking to design for when we're thinking of geometric models. So those are kind of the first two things that we look to understand about any room that we're designing. And the other sort of more complicated concept would be sort of hotspots or dead spots in the room. And that could be either caused by geometries that tend to send sound to one specific seating area and not others. So in a larger room, you can get areas where it's really loud in some areas and other areas can't really, they don't get the same level of envelopment. And then in smaller rooms, it can actually just be because the sound wave itself is so physically large compared to the dimensions of the room that it's going to build up, the sound pressure is going to build up in some areas and not in others. So when we think of putting together a model, the first thing we do is put together the geometry.
Here, I'm going to interject. Who doesn't build geometry before they build a model? Thomas, do you start with anything else but geometry in your models, or do you get to reuse anything that like the architect gives you?
I mean, if the architect has a very good model already and take that geometry and transfer it to my software, I can do that.
Yeah.
Otherwise, I would stress.
How about you guys? I mean, interoperability is a huge other topic, but just want to see like who in this room builds geometry basically for any sorts of model. Right. So majority. So it's like pretty basic that we have to like first look at ourselves in this 3D environment and then.
In this case, do you get geometry from the architect you're working with, or do you actually build your own geometry?
It depends. Usually we take CAD plans and sort of extrapolate from there. Because the sort of Revit to acoustic model transformation doesn't tend to work as well because we're interested in different things in the model, right? That for a large surface with a lot of detail, maybe we can approximate that by giving it some scattering coefficient. But what we do need is for the model at the end of the day to seal airtight. And I think it's the same thing for energy too, because we're interested in how the energy transfers around in that room. That really needs to happen. It's usually just a more efficient use of time and effort to just build it from scratch and know that it performs the way that we need it to perform. But yeah, that's jumping ahead a little bit. So the first thing would be actually creating geometry, pretty typically. And then once we've sort of put together all of those planes that are going to form the inside of the room we're looking to understand, we ascribe it those surfaces of absorption and scattering coefficients, which let you know that when the sound hits those surfaces, sort of how much is sent back and how much is sort of dispersed randomly. Sorry, stay there. The other thing that we need to do when putting together one of these models is determine where the source and where the receiver is. So sometimes that would be, those are various source locations for this specific model. And then we had selected a couple of receivers in the audience area. If we go back a slide real quickly, we can also select sort of areas, audience areas to compare different zones with one another. So that would be sort of the process of how we like to put together models for acoustic purposes. Okay, I think, next we're going to jump into kind of how we did this before we had all of these tools, right? That people built buildings that worked for years before we had these computer tools. And in the sort of general definition of modeling, this is modeling as well, right? We have these mathematical models for how a room is going to perform, and we need to understand those before it's built. So Wallace Clement Sabin was the grandfather of acoustics, who was basically tasked with fixing a bad lecture room and ended up creating a subdiscipline. So this is on the right, it's actually a slide from one of his papers, putting cushions in a room and understanding how long it took for the sound to decay from a loud impulse all the way down to nothing, or perceptibly nothing. So that was a good general tool for understanding how sort of generally live a room is. But it doesn't tell us a whole lot about specifically what different parts of the room are doing. The next sort of analysis method is geometric ray tracing. So that's assuming that sound behaves like a ray, which it's not going to, but for high frequency sound with very short wavelengths in a big room, it's a good general approximation. And then the sort of the final sort of pre-computer modeling method that we would do is actually creating a physical scale model, which obviously gets a great amount of detail. You're able to sort of mimic actual measurements we'd be able to take in a room by creating a little sound source on the stage and having small microphones, and then sort of extrapolating out over time how the actual room would sound. Obviously, putting together a model like this is not something that's done very quickly, and it's not done very easily. And except for the largest projects, computer modeling is definitely the way of the future, based largely just on the economy of time and effort. So,
which one is the most effective in the results? The physical scale modeling or the computer?
Sometimes it depends. It depends on what we're trying to look at. The physical scale modeling would certainly give you the most realistic picture of what the end result is going to be. And I think what's going to come into our conversation later is sort of how useful is that really when we're trying to pick out individual elements that we're looking to design. So a computer model is certainly, you could quickly say, take out all the ceiling reflectors and see what's going to happen, right? How's the room going to sound? But providing tweaks to the geometry in a model that you've already built is a lot more time consuming. So
we can say this part because, like, I think almost everyone here appears to be aware of what the energy modeling is, just judging based on the looks on their faces. But basically, we do that to either predict or simulate how much energy will be consumed for keeping us comfortable, what kind of equipment will be placed, and how we size them. how we orient and optimize mapping, shading, a million other things, and active passive strategies that can lower those energy bills, plus how are we checking if you're achieving thermal comfort or not, and seeing if there will be condensation are main things. And before we got here, basically again, just like Hans said, there were buildings and without any calculations for energy or loads or anything. HVAC is also like relatively new field. But before HVAC, people were heating and cooling themselves passively throughout the ages without any calculations. The first calcs for this appeared in 1920s as response factor methods, RFMs. They evolved into the actual load determination, and the word got coined in the 1960s. And with the energy and oil crisis in 1970s, just basically things picked up and actually got mature, and now we have load calcs. And load calcs was, I think, like the beginning of the energy model, and just they added time. Now we have energy model. With the we're going to be doing this most of the time. Bit of acoustics, bit of energy.
Okay. So jumping over real quickly to sort of what kind of computer modeling we do. Touched a little bit on sort of various issues that we encounter in acoustics, and there's different modeling methods that are appropriate for different uses. The most common thing you'll see in the image here is sort of a ray tracing solution, where similar to the actual geometric lines on the two-dimensional drawing, it approximates sound as just a ray. And you take a huge number of these and shoot it off in every direction. And then as those bounce around the room and then recombine at various receiver locations, you can understand the timing and the strength of those reflections. And that's a really great tool, and what we use most of the time for bigger rooms. It's good for approximating high frequency sound in a big room. So if it's a big sound wave that's encountering something that's not that big, it's not going to reflect back, like a mirror would reflect light. It becomes a little bit more complicated. The image source solution is a great solution in terms of the computational sort of accuracy of it. What it does is it basically treats each of the planar surfaces as a mirror, and instead of looking at geometrically what reflects off of that surface sort of as it goes around the room, it uses it as a mirror and then creates an imaginary source that comes in at a later time. So usually we'll set up this solution to recreate the early sound because it is so accurate, and you're not going to miss a reflection from a major surface between a source and a receiver. But as you increase the sort of order of the mathematical order of the image source solution, it explodes. So much beyond 3 orders, it's really not computationally efficient to run a model that way.
Just as an analogy, like in radiance modeling, if you ever use a mirror tool, like the mirror material, you can have so many mirrors. After a while, it just will not. You're not going to get any result because of the same thing. In radiance, the mirror material just puts the sun at the total opposite direction and then just recalculates instead of trying to rebounce the image source. Does the same thing for this.
Ray bombardment I have here, real quickly, is basically a very simple version of the ray tracing solution. So we had a software script developed in-house that allows us to just select the ascending position and then a surface, and then you could say, I want to see what happens, 1 reflection off of this surface. I want to see what happens, 2 reflections off of this surface. And actually, if we jump back to the previous, that slide, there's an example of where that's been done, which just gives us an idea of how a surface is acting in a room. And that's something that's more of a design tool than it is necessarily a model of the acoustics. And then the last thing, going back quickly. would be finite element analysis or boundary element analysis. So that would be for conditions where you have big waves in small rooms. So if you have a recording studio and you need to mix a lot of low frequency sound, those sound waves are going to be really large compared to the size of the room. And you want to make sure that you're treating the room so that you don't get large peaks and valleys at different locations, because that would affect how a sound engineer is going to be able to accurately make mix choices in that space. So going back, this is just looking at sort of what the outputs are for the modeling methods we have. There's the simulated impulse response over here on the right, and that's basically looking at the timing and strength of various reflections from one source to one receiver point. So that allows us to look at it and see sort of when reflections are coming in, if we think that's going to be a problem, and then to try to tweak either the surface location or material to deal with it accordingly. We saw on the previous slide was an example of mapping, which just shows the sort of level gradient at different locations. There's a couple different ways we can do that. In smaller rooms, that would be sort of an example of a standing wave. In larger rooms, we can actually look at timing slices to see, for the first 50 milliseconds, how each person in the audience, gets reflections from the various surfaces of the room, and then look to sort of treat problem spots that way. Oralization is a real hot topic. I know there's some Arab folks in the room, and they're very big on that as well. It's a useful tool to show a client basically how a room is going to sound. So it takes the directionality and the strength and frequency content of each of those reflections, and then combines it in a way that provides an approximation of what the experience would be in a seat in the room. I think Joseph Myers likened it to a watercolor sketch of being very useful for giving people an idea of what a space is going to be. In terms of, I was going to say, in terms of a design perspective, it's sometimes more difficult to pick things up that way, but that's more conversation for later. And then the last is just the geometric ray tracing, which I touched on. Being able to do that in 3 dimensions is way easier than trying to trace things individually.
So just like Hans, there are various forms of modeling that we can do for energy, and they basically vary on scale, complexity, and reasons of modeling, etc. For instance, if you're only trying to get the peak size, and you would do a dynamic thermal model, you would do Pico's model, and they would be different in terms of inputs and also outputs. And if you wanted to do some rapid fire parametric modeling, you would build a tool in a different way. And if you wanted to see localized impacts of how air moves inside the space, you pretty much need a computational fluid dynamics model. And for some real small details, there's like Hans' slides, and he said, in a smaller model like a recording studio, they need the finite element method. Same thing for us, in a small component of the building, such as the curtain wall details, then we need the finite element method, what we call the thermal model. And we basically solve for the surface temperatures of each component. Well, again, like the main subject we would like to touch on is when we think it's appropriate and when we think it's not appropriate. Basically, like you can start with this.
Okay. Yeah, so I think that the first thing, I spent a lot of time sort of walking through each of the different modeling methods. We just need to make sure that what we're trying to understand about the room can be understood with the tool that we're using. And that maybe it can't be, but that it's the best tool to do the job.
And then again, like referring to the 1987 code, old are wrong. If the question requires us to have no approximations, if there is like the precision and accuracy is like really critical, then we shouldn't be building models. We should be building the actual thing and testing it.
Okay. Yeah, and on that line of thinking, there's a lot of times in the consulting world when creating a model, it takes a lot of time. We might not always have that time, and more importantly, we might have a huge bevy of experience to rely on. So a lot of times, when a design is kind of similar to something else we've worked with before, we might not necessarily need to create a model for that condition. We understand the positives and the negatives of that design, and we can work with it accordingly.
And even sometimes, let's say, we fully know what's going to happen, and we tell the client that is going to happen. Still, there are times that the client needs convincing and persuasion that it will happen. Not that they don't trust us or anything, they just believe it when they see it. And that's when we revert to modeling, even though when we know exactly what the results are going to be, to show them, to visualize what the output is. There's a lot better ways there to visualize something unseen, like air and like sound and energy, than to like do a model and put some pretty colors to it. Amazing.
Yeah, and then the last is for clients who really have just the absolute highest expectations of what is going to be done. Having the latest state-of-the-art technology applied to understanding their space before they have it delivered is often a high priority.
And of course, if any of these are not true, then you wouldn't model. For instance, if as I said, like if it cannot be approximated or if it cannot be put in a representative model, then it is unmodelable. And there could be some situations like that, right? And sometimes, just as Sam said, project has really low expectations, project high or decline, and they're merely asking for our advice, our recommendation. They pick up the phone and say, "Hey, what's your gut feeling about what if I do this?" You're not going to say, "Okay, give me 5 days. I'm going to model something and get back to you." You would just give your best advice based on your experience.
Yeah. And along with that line, besides just the low level of intricacy that's really desired in the design process, a lot of times that's tied to schedule as well. It takes a lot of time to get a model off the ground, to get it running, but more importantly, to really explore it and work through design choices. You need to have that time to let the model run and to compare results. And if you just have a tiny schedule and everything needs to get done immediately, inevitably you're going to need to depend more on some of that existing experience that you have in house.
So we would like to pose you the question, because I see some of the consultants here, like when would you revert to modeling, and where were the times that you decided not to model something and just go with experience or gut or a rule of thumb? Any takers? So you always model?
I think it depends.
Yes.
Both on the complexity of the problem and on the sensitivity or critical nature of the use for that space. So, if there's a utility closet, there's no need to model the sound there because you just do a rough calculation and ensure that it meets whatever standard. And that's generally good enough if it's a critical listening room or auditorium. Talking about sound, but a similar analogy would apply for energy modeling. You have 20 offices and they're all within 4 square feet of each other. You don't need to make a model for each.
And sometimes it's kind of the part of the procedure. For instance, of course, there's a way you can get a leak flag without doing some energy model with the prescriptive methods and etc. There are times where models are just built for like bureaucratic reasons, and sometimes just to pass the code, they have a larger window-to-wall ratio that they cannot restrict to the code, etc. So I feel like, at least us, we almost always are doing like an invisible spreadsheet behind our head for decision metrics. Like, what should I do now? Like, do I go start modeling, or do I do something else? Do I reach out to others in my firm and ask, like, what would they think? Or just, like, I feel that's something that there is no formula for. Right? We haven't all figured it out, but we're also like trying to not only do what we have been doing, also. So when we run into something new, that's more excited, more curious, and we would be tending to model something just because we would think we would learn from it too, not just the architect or not just the client. So that has been some of our more eagerness to model, even though, let's say, we don't have a fee, we do it anyway. Like, that has something too.
I would question your comment though on modeling something that can be modeled. There's oftentimes you do want to model something that can be modeled, or at least show the risk or elements of the modeling process that allude to that risk that you can't necessarily fully capture in one element of the analysis of the model, but maybe it's other elements of analysis that would lead to that. So, and I think that also pushes the boundaries of modeling, and what advances the developers of software or in-house scripts or whatever.
And then usually it is meaningless unless you compare it to some measured either experience or data, right? So whatever the model tells for RPI, if the people who go in there to listen to a piece of music, if they're not happy, then they're not happy with whatever the model said. Or if the building you're trying to model is consuming more energy, if the utility bills are showing that, then basically what you have done has no basis. So models on their own, of course, like, this is gonna sound Captain Obvious, but they don't have to be like the things that is gonna enchant and like make believe and get us paid. It's always like need to be benchmarked against something, and calibrated models for energy analysis is big nowadays, called like measurement and verification. I'm not sure if similar things that you do in acoustics. So.
Yeah, I mean, certainly working on models of existing spaces is always a good opportunity to be able to confirm a lot of the sort of coefficient selection for services. When you've actually seen the services, you've measured the room in a certain position, and then you're able to compare the real thing to this, what we know to be a useful approximation, and getting those things in line with one another. I think is an important step that it's good to do whenever possible, and that helps make some of the more predictive modeling all the more useful, that it can be relied upon. A lot of times, we like to work with mock-ups where things sort of test the limits of modeling capabilities. Like to work with real physical materials as much as possible, because there are a lot of approximations that go into the acoustic modeling process, just to make, again, computational, just to make it work, and having that real world experience is also useful, I think, for the client as well. If it's something that you can share with them, so that they can actually see real results from real materials. And as the modeling versions and computer capabilities get better, that's going to come closer together. And I think a large part of the reason that we're talking here today is to just really discuss sort of that, how far away that is, how close that is, how useful these tools can be, working towards that moment, understanding where we are along the way.
So speaking of sort of using the model and predicting future advancements, how often you guys work with existing structure, existing buildings, and actually implement, or in this case, choose to implement a model in order to track various changes or additions or revisions?
Yeah, I mean, a lot of our projects are existing projects, and we'll do that. I mean, especially for primarily performance spaces, or where really that level of attention and that level of analytics is necessary to do that. I'd say our project mix is about 50-50. So
when we do existing building models, especially for energy, then we have a perfect understanding of what the building is already consuming, right? Because the utility bills are already there. And then what we usually end up doing when we quote unquote calibrate our models is just to like tweak a few things until we get there. And that gives us greater confidence than a model which is not calibrated, but it's still not the actual thing. Because again, like there are so many inputs go in there, such as the occupancy, that you actually don't have a clue about. Because you're not sensing the people movement and you're not counting how many people in the room. Like there's no way anybody in this building knows how many people we are here right now. So that's why I'm kind of sweating. So that's all part of the equation. And there are more things to touch on. So there's actually the shoebox models, which is, I think, an important step, and it's not included in the slides. But before we build anything that resembles this, it would be great if the modeler himself or herself gets an understanding of what the physics will be in the thing that he or she is building. And there's more and more, basically, recommendations and encouragement towards this, what I call shoebox modeling, like sketch models per se. Even the newest lead version basically gives you a freebie point if you've done a sketch model, like whatever the outcome is. So we are going to show some examples of the large scale models, but just wanted to say that also like the baby steps are also as important as the big picture again.
Do you tend to, like, kind of related to your last slide, the Wendy model, do you tend to do these type of shoebox studies earlier on in the process, which might reveal like sensitive issues that you could change the acoustics of certain panels or room geometry? Is there like sort of maybe big things that would definitely influence the design process?
Yeah, of course. Like it's almost like the BIM execution plan has a 100 level, 200 level, 300, 400, 500 level models, right? So you don't start modeling everything in the first conceptual stage. You wait and you design and then you model. Sometimes you design as you model, sometimes you model as you design. In many cases, with my work at Real, we've been building many smaller like sketch models that look so trash but are so valuable. It's especially the one in PNC. We're trying to get to a solar shafts, and the quick models we had done without the entire building, but just like a long shaft and a few zones here and there, just cluttered, told us a lot. And we keep doing that. And the latest one, actually, that I did basically deferred us to a completely different path, and the whole design changed in one of the last shoebox models I've done. And even like having the confidence to show that to the client and say, what the path we're on does not make sense. We have to divert early, and we have to do it now. So that's the main value of the early models. How about you guys? Do you build early models, or do you wait till the last stage of the design? Or do you wait until you get a phone call that they need a model yesterday?
Early ones, not a structural.
You're a structural.
Yeah, we definitely have like more sketchy models. But right now, I think there's so seductive with the whole BIM
Mhm.
discussion, and you see this whole Revit model to try to bring that in and see it and build like this full model, but then it always ends up being really time consuming, and you just have to get quick answers and that's,
Yeah.
the feedback with the design, like you're saying, they need to know whether the path they're going on is the right one or not. And you take the time to build this new model, you're not going to get the answers they need the time.
Time's always.
So we do need cash models. The other thing is like choosing the right tool, because there's so many tools that are good at one thing and not so good at the other, and so we end up building like 3 models sometimes. All based exactly the same geometry, but we need one software to do that, or software for the graphics. It's like there's so much thought that has to go into that in the early stages of that out. How what they're going to model, and how big the model is.
Yeah, I mean, for acoustics, I think a lot of the sort of early steps of modeling can be done with some of those pre-modeling tools we were talking about. Just actual spreadsheet calculations, two-dimensional geometric studies. A lot of times that can give us insight to know if we're on a direction that's, that can be massaged into shape, or if it really is just not working. And even those studies can be enough to really sort of demonstrate, versus other benchmarks of, comparable halls, comparable spaces that, they're seeking to have their project perform like, where things are coming into alignment. So really, yeah, early models only happen if there's a design direction where there's a lot of momentum rolling in a direction that gets us very uncomfortable. And then maybe at that point, we'll put together a more complicated, geometric model to really demonstrate that maybe this, design idea is not the best way to go. And if we went in another direction, we might be able to push things into a better place. So,
Do you want to move over?
sure. So this first modeling example is sort of more of a later in design issue. This is the University of Iowa Hancher Auditorium. It's a large multi-purpose auditorium. So it has it's a large, tall space, and we needed the reflector elements in the house to provide sort of overhead reflections for the entire audience area. That was going to be at an appropriate time window, and that we weren't going to have areas that didn't get a reflection and areas that did, while still only having, as you can see, not that much area actually covered by those surfaces. So first thing is sort of a wireframe isometric view with one of the source locations we looked at. And then on the right, we have a sort of overhead plan view of the seating area. So this is actually taking a look at, it really is just the ray tracing module to see what the coverage area of each of these elements is going to be. So the large overhead reflector covers most of the floor area for this source position. The next one has a good healthy overlap there with this first reflector, and then sends out further. Now, one of the unique things, actually, we could double back to the one before. You'll see here is that these reflectors are curved and planned. So just looking at a centerline cut is not going to give us a good idea of how those are going to behave. Looking at, maybe a cut a few feet over, might be useful. Going all the way to the edge would be even more useful. But even if we went through all of those exercises, we still wouldn't be able to understand what happens when you move off center, and how that disperses over a three-dimensional bowl seating area, over the whole audience area. So what happens here, the as the reflector turns around, it's flatter in the center to give a stronger reflection over this zone, and then becomes more tightly bowed at the edges, so that we make sure that we really treat these areas. Yeah, if we jump to the next one. So this is the first catwalk reflector, which is a completely curved element. So one of the things we're really looking at is to make sure that we had good coverage overlap there, while we were still able to sort of flatten this this second reflector as much as possible in the middle. And then we also have overlap here between the second catwalk reflector, which is also a curved element. And then last but not least, we have the upper ceiling, which provides that overhead reflection for the very last seats in the house. So an example of something that if we tried to do this on paper, this would have been a month-long project, at least. But you know, getting this 3D geometry defined and being able to select sort of a few locations as we go, we're able to really understand how those elements are going to behave in a lot of ways that we wouldn't have been able to 15, 20 years ago.
And now I'm going to show another model. What do you know? It's another performance wall sign. We're just looking at the geometry, but even this taught us a lot because, again, it was a curved balcony. This is for the Utah Performance Art Sign. And we had selected a tool that we had perpetual licenses since like God knows when. And I was thrown this software to say, well, learn it as you go along. Come on, you can do it. Basically, what it turned out was like this tool was not the right tool to build anything this complex because building the geometry in-house lasted forever and I got yelled at every single day. But it wasn't my problem, so I was happy getting paid. And then the elements we were slowly adding and adding to the geometry included drapes that are fundamental for the absorption coefficients that he was talking about for acoustics purposes. So this is not their project, but he knows what they do more than I do about reverberation, whatever. But basically, it also hindered the airflow, and adding them later on also like gave us more and more resolution as we were adding to the geometry. But geometry is not the only thing. In a CFD model, computational fluid dynamics model, the loads, especially for a sealed zone like this one, which had no exterior connections, with internal loads were the single most dominating force. And one of those were the performance lights. And they were so intense, basically the orange blocks are representing either where they are or where they are pointed at, because there's a convective part of the light load and then there's the radiant part of the light load. We were to capture both. Basically, all these are our catwalks that basically have those like really long lights that they point everywhere for the performances, and these are where they are radiated. And this is like the upper ceiling where also so many lights are being housed at. And we had also learned in this process that turning on the house lights, the architectural lights, at the same time as the performance lights would never happen. So basically, we took the largest of the evils and then went with it. Another dominating force, much dominating force, is the audience. We do generate heat, even when we are watching opera and Smorey. Still they had to be basically modeled as the watts per person, which are modeled individually for each person there. So maybe Hans would model them as, again, like absorption coefficients over the, but for me they're just heat sources. And I had to build the shoebox model here because in order to model a person on a seat, I had to know how much resistance it has to the air. So basically, I actually took the person sitting model in a very like small scale and ran a bunch of air through it, and then basically adjusted a box that represents the whole thing without all the shoulders and head and legs, but it does exactly behave like a seated person in terms of restriction of air. And that was one sketch model built for this one. And supply air, this was obviously under for cooling, and return air. This was a main design driver because the earlier iterations, we had not included the return airs at the, like behind the first level. We had only relied on the upper three and the top one above the stage, hoping it would do the job, but it wasn't the case. I'm going to get to that. And overall, it looks like this when you overlay everything. And of course, this computational fluid dynamics model basically models every grid cell I put in there, and there's basically representing the volume and the air inside the volume, and solving for temperature, speed, and direction of speed, therefore velocity, among other things. And this whole volume has data, and the best way to show this data is to cut a slice and pretend it's 2D. People work better with 3D sometimes, but when they look at computational fluid dynamics, 3D doesn't work. We have to give them like slices, either plans or sections. Then it becomes more understandable. And that's the slice we're looking at, that red point. Now this was the first iteration without those return grills at the first level. So we would see considerable heat buildup, reaching 80 degrees, hottest spot anywhere where the seats are. And that was pretty much not only undesirable, but also would give the very bad impression as you step in. You'll get that if you're getting a hot air, you're also probably getting stuffy air, so carbon dioxide and everything else would build up there. So that's what it told us. So we saw that, made changes. This is before that change. We've here, I did another thing which I forgot. I think something to do with how the ceiling was behaving and the lights were. I think that's when we turned off the architectural lights. And here we've added the drapes, which were also interfering with the air, and we should have in the first place. And here you can see how well like that condition improved. And this was not the only section we're taking. We're taking it like 5-6 sections through this volume to show, and also to see what's going on, how it's behaving. You can see that also another major improvement was at the stage level, where we didn't increase the cooling capacity, but we basically just increased the speed that the drum blowers were shooting air at. So this became that, if you look at where the stage is, a considerable improvement from this overall heat room to much preferred conditions, just by the same energy used in a smarter way. And then the last iteration, after many other things, the client wanted to have capacity so that they can freeze the people if they wanted to. And that was our modeling for the CETA thing. And the things we learned, basically, again, like don't do a complicated model in a 1980s software package, and communicate as much as possible within the team so that the energy you input is used in the right place at the right time, and then know all your consultants and how much heat they're going to input. There are some consultants that might not put that much heat, like an acoustic consultant, but lighting consultant will. So listen to them, what kind of equipment they're placing in your space. I can do shows nothing but arrows going. It's actually this, even though this is a steady state model, meaning there's no time to it, you can still animate the life of a particle, and you can show them where air is coming from and where it's going to, and how it's all well balanced. And if you can't see that, this is easier to see. Arrows going in the right places, everyone is happy. So another example like a.
Okay, this is another example. This is using the a different problem. So here we have a small audio control room, and we're looking to make sure that they're able to mix in the room without having really high levels of bass in one area, and then they move their head 6 inches and they're suddenly at a pressure minimum and they can't hear it at all. One of the specific challenges here, this height, which isn't identified, is 8 feet. And that's specifically challenging because everybody's ears sitting down are right at about 4 feet. And then take it from there. Once we had that, we were able to create a model, a pretty rough model actually, from earlier on in design, to understand how sound pressure was going to build up at those frequencies. So as that modeling method solves for the wave equation, what we get is a mesh of points with different levels of sound pressure as they're excited. You can actually see at the sort of loudspeaker positions here, and then we also had a subwoofer. So this is looking at 68 hertz, which is one of our problem frequencies. We can sort of see where the sound is tending to build up. At the front bottom of the room, it's taking down the middle, the rear bottom of the room, and then at these sort of front sides. If we flip to the next.
Is that like a computational companion for the acoustics?
I think it's a little more detailed than that because it's basically finite.
So, but of the types of models that you have, what would you call this one?
This is the software package, it's ABEC, which is it's a boundary element calculation, acoustic boundary element calculation. So yeah, if we flip back real quickly. Oh, no, sorry. Oh, no, one forward. Okay, so then we at another potential problem frequency, looked at sort of how sound is going to tend to disperse around the room. And we have less of a hotspot at the front, but we have the same sort of at the lower rear part of the room. And at these sort of, these wings along the side. And then jump on to the next one. This is, I mislabeled this. I think that was at like 112 or something. But you know, we're similarly, you know, it's a different pattern, a higher frequency, so there's going to be more pressure maximum and minimum. But we get a little hot spot at the rear of the room here. We still have those hot spots at the sort of front wings, and then a much larger one here at the front. So if we flip all the way back to the design, this layout is repeated at the front and the back of the room, basically. And what we have along the bottom here are tuned bass absorbers, which are specifically tuned to the kind of frequency ranges that we were concerned about. So by having these models available, we're able to understand sort of where the pressure is going to tend to build up the most. After we'd identified those locations, we're able to tune bass absorbers that we're going to specifically target those frequencies in locations where they're going to be problematic. If we flip back before also as well. Here is a little, it's basically fabric wrapped absorption panels here. What we've done at this middle zone is actually step the hard architecture back so that we're able to get a really large airspace and get some lower frequency absorption there. So
we're just gonna touch base on how all subjective this is. Basically, somebody can say a room is loud and somebody can say it's quiet. And it's the same true for hot and cold. And basically, at the end, whatever we propose, the client might say they don't like it,